Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so what we're hoping to do today is get a really broad view of what's going on in designing servers for tail latency and batch and cloud, and connect both some of the workload characterization with what people are doing in systems. And so that's why we have speakers from all over academia, and we have a lot going on at Microsoft. So we also have quite a few Microsoft speakers, but most of us are going to be in the 3-minute madness session so that you all get a notion of what we're doing in research and also some of the things that are going on in products. So your job is to give your talk and on time and stay in your 15 minutes, and I'll have a I'll have a timer going, and I'll turn it at you if you're abusing it. And also to think about, after you discuss among your table, think about asking questions for the speakers or just comments that you want them to respond to. Or if you just want to pontificate, we'll have time for that too. All right, are there any, and then there's coffee around the corner. Our local coffee stand, unfortunately, is not. You shouldn't come sit with us at our table, so we'll have someone else to talk to. Thank you. But around the corner, you saw that there's still coffee. So hopefully you can, if you need it in the middle, feel free to go out. Oh, thank you, Jan, for coming. All right. So our first speaker is from the University of Michigan and sometimes Google in the summer. So we have the enemy and the, he's here as his academic role.
That's right, I'm here representing Michigan. Google had nothing to do with this, despite the fact that there are 3 Google names on the title slide. So does this mean I get extra time, Kathryn, because I'm starting early? All right, well, so thanks for the introduction, Kathryn. So I'm Tom Wenisch from the University of Michigan, and like many of you sitting in this room, you know, I have a 60-minute talk, which we're somehow going to do in 15 minutes. So this talk, Killer Microseconds in the Tail at Scale, is actually sort of a little excerpt from a keynote I gave about a year ago. And this falls into the class of research I wish I were doing as opposed to research that I have done. So what I'm going to talk about today really is problems, and mostly just the killer microseconds problems that I wish, you know, I would like to solve, and some solution directions, but I have no idea how to actually solve this. And so in a nutshell, the idea of killer microseconds is that because of advancements in hardware and networking and so on, it's now possible to have data single-digit microseconds away from the system that would like to access it. But it turns out that we're really bad at designing systems to tolerate microsecond scale delays. And so I'll talk a little bit about that. I won't talk about the tail at scale, but I'll at least give you the nugget right now. Tail at scale is the idea that when we think about sort of our large-scale distributed systems like web search, ad serving, and so on, there's hundreds to thousands of individual servers involved in serving each user's query. And at that scale, rare events will happen on one of those servers every single time. You'll have a 99th percentile latency every single request because there's more than 100 servers. And so, we used to say make the common case fast and make the uncommon case correct in computer architecture, but now the uncommon case is the common case, and so you really need to reason about very rare tails because of the scale of the systems that we work on. So if you want to hear more about that, come find me in the hallway. But I'm mostly going to focus on the first problem. And the class of workload that I'm really talking about here are online data-intensive services, which is sort of a cute term that we coined at some point for the kind of workloads that I think all of us here in this room think about. It's workloads that have the challenge of processing terabytes of data in millisecond scale latencies because there's a human at the other end of some web request waiting for the response. And so there's lots of things that fall into this class. The classic example is web search, but there's lots of other things that need to process terabytes of data in millisecond timescales, machine translation, online ad serving, all of the things that we would think of as interactive web applications. And what's important about these workloads is that we really care a lot about tail latency, right? We really care a lot about 99th percentile response time, and that sort of changes the way you're going to optimize the system. To some extent, mean latency really isn't the most important metric. And the reason that these have to be scalable distributed systems is the only way you can actually process terabytes of data in millisecond timescales is if you have 1,000 computers involved in processing that request. Otherwise, you simply can't meet the latency constraint, okay? And for this class of workload, efficiency is really hard to achieve. It's really hard to operate CPUs and other aspects of the system at high utilization because there's lots of interaction. There's lots of I/O from one system to the other, from sort of some root node that's fanning out the request, or accessing some data off of an SSD and so on. And those frequent I/Os cause a lot of stalls, and that adds up to a lot of time. And we also have to really worry about queuing effects. Queuing effects will rapidly cause tail latency to grow, especially if you try to put the utilization on the servers really high. And so the net effect is that we actually operate these things at comparatively low utilization when you think about, in comparison to supercomputing and so on. And I think there's really two challenges going forward that we as a systems community need to address to try to get higher efficiency. I'm going to talk about killer microseconds. That's the idea that we really don't have good solutions to microsecond scale stalls. And as I said before, I also think we really need to worry about rare hiccups that become the common case in distributed systems. All right? So, in just 10 minutes here, let me tell you a little bit about those killer microseconds. And sort of the backstory here is that hardware designers, in the computer architecture community, I'm a computer architect, have been extremely effective at dealing with nanosecond scale stalls, right? We have, it takes 50 nanoseconds to access memory, and we have lots and lots of techniques that are very, very good at making those 50 nanosecond stalls disappear. We have caches, we have out-of-order processing, we have simultaneous multi-threading, we have prefetching. And all of these techniques, serve to hide those stalls, and a lot of them rely on parallelism. But the key is that parallelism is transparent. From the point of view of the programmer, we have a single instruction stream, and magically, the hardware hides all those stalls through all of these fancy mechanisms, and we have ordered loads and stores. That latency goes away. If you go to the other end of the spectrum, if we think about sort of disk accesses and what traditional techniques we've done to deal with the latency of disk, so of course disk is multi-millisecond latencies, and the modern operating system is astonishingly good at hiding millisecond scale stalls, right? What do you do when you have a millisecond scale stall? It's simple. You just switch to another thread. And as long as we design our software with sufficient thread level parallelism, some sort of transaction processing system that has lots of threads going, or web search that has lots of requests, that request level parallelism makes it possible for us to get very good utilization out of the CPU, despite the fact that disks are pathetically slow. Okay? So again, we're relying on parallelism here. We need lots and lots of requests. But if you think, again, from the point of view of the programmer, the parallelism is largely transparent because we write single-threaded code on one thread, and the operating system transparently swaps that thread out when we have this disk-level stall, and we can sort of write a synchronous I/O, and everything works wonderfully. All right? What's changed? So the thing that's really changed today is that modern I/O devices are now mere microseconds away. They're not milliseconds away anymore as we were in traditional disks. So if you think about the data center network, within the data center, data is, say, order 25 microseconds if you have to cross the data center network to get it. If you're getting something out of remote memory, if you have a solid-state disk, maybe we're order 100 microseconds, and that's getting faster. And there's promise of faster NVRAM technologies coming, right? We have Crosspoint 3D that should be coming sometime next year. And if you think also about accelerators, things like Google's TPU, accessing one of those things is also sort of a microsecond scale delay to submit work and perhaps wait for it to come back. All right? So now we need to worry about hiding microsecond scale stalls while we're trying to access data. So what's hard about this? The reason this is hard is that the abstraction that we would like to give to programmers is, again, parallelism is transparent. We would like to give synchronous I/O transaction. Even I can write the code here, right, to access data from a disk. Turns out that that's sort of within the capability of what I can write. That far side of the slide there shows you the equivalent code to do exactly the same thing, just read 100 bytes, using asynchronous I/O. This happens to be code for Windows, but if we, because we're here at Microsoft, but if we looked at sort of the equivalent code on Linux, you'd end up with a similar eye chart. And that's a disaster, right? No one wants to write the code on the far side of the slide. It's much, much more complicated to reason about control flow in the context of asynchronous I/O. But that's really what we need to do today if we want to try to hide microsecond scale stalls. So we think about what should you do sort of with your CPU when you get to an I/O that's going to be answered in, say, 20 or 30 microseconds. What are your options? All right? And at a high level, there's really two approaches that you can take to try to deal with that microsecond scale latency. The first sort of higher performance approach, higher performance from the point of view of the thread that's doing the I/O, is to actually spin, do nothing else with that CPU, and wait for the I/O complete. All right? So if you're going to do high performance I/O, you're going to use some kind of operating system bypass I/O solution where you're spinning on a completion queue, basically a shared memory location where you're waiting for some signal from your hardware device that tells you your I/O is done. And from the point of view of latency on the thread that's trying to do that I/O, this is great. You have very low latency to dispatch the reply. The moment the hardware device comes back and says in memory, hey, I did the thing you wanted, you determine it right away at just the latency of a shared memory exchange. There's no hardware interrupt, so there's no overhead of trying to go into some weird part of the operating system to process that hardware interrupt. And one of the very important points here is it's clear where processing should continue. The thread that's waiting will proceed and execute the continuation after that I/O succeeds because it's sitting there waiting. You don't have to make a decision about where to run that code. You maintain all your cache state hot because nothing else can show up and take that CPU and stomp on it. And there's also a very low risk of the operating system coming along and sort of being a troll, taking away your CPU because you're spinning actively. It looks like you're busy. The operating system doesn't get the bright idea of deciding that, maybe you should go to sleep. So that's great for latency. But it turns out it's terrible for utilization because all of the time that you're sitting there spinning, waiting for that I/O to come back, the CPU is doing no useful work. And if this were a 50 nanosecond stall, who cares? But once we get into the sort of 10 to 15 to 20 microsecond scale, if we're going to do this every, say, 10 to 50,000 instructions because we're interacting with some remote storage, you're going to waste a lot of time doing nothing, just spinning. All right? And CPUs are very good at spinning, but it turns out that not a lot of forward progress happens. And not only does spinning on your CPU waiting for your I/O to get completed waste the CPU that's doing the spinning, it turns out that in current CPUs, it's also a remarkably trollish behavior for the hyperthread that would like to co-run on that CPU because while you're sitting there furiously spinning away, you're taking away instruction issue slots and you're also taking away hardware resources that could have been used by that other thread. And in fact, even if you spin really slowly, one of the recent results in Kathryn's work shows that even a super low IPC thread by its mere existence alone steals an enormous amount of resources from the thread that would like to co-run with it. And finally, there's a limit on the amount of parallelism. I can only spin on the number of cores I have. And so that places a bound on the number of I/Os that I can wait on with low latency. All right? So this approach is trading efficiency, giving up CPU efficiency in order to get really low latency. Okay? But of course, that's not the only solution. If we would like to try to get some of that CPU efficiency back, we can do what we did with disks, which is we can block in the operating system and take a context switch to go find something else useful to do because there's probably some other runnable thread and use an interrupt-based mechanism to find out when that I/O is complete. All right? So here we go into the operating system and we block and we wait for an interrupt. And of course, the win here is now that CPU is available and can go do something else. Right? But that's the only win. It turns out that we pay an enormous price every single time we step into the operating system to try to find something else to do, at least in sort of modern Linux, and I think the behavior on Windows would be very similar. There's sort of a order 5 microsecond direct latency impact simply to execute the code of the context switch. If you're heroic, maybe you can get this down, but if you sort of measured this in just sort of open Linux today, you'd get a 5 microsecond latency. That comes from things like the fact that you have to take a hardware interrupt, and that interrupt invariably goes to the wrong CPU because the hardware just routes it wherever it feels like, and so then you've got to do some kind of cross-call nonsense to get the interrupt to the CPU that would actually like to run the driver code. Then you have to wait for the OS to schedule the second half of the interrupt, and all of these things end up burning sort of microseconds of time. But that pales in comparison to the cost that you pay as a result of having another thread having run on that CPU. It's just sort of pooped all over the cache state brought in all sorts of other stuff into your cache. And now IBM did a study that showed you could take up to a millisecond of extra latency when you run that continuation code after the I/O comes back, because of the result that you're taking a bunch of cache misses because some other thread came in and sort of disrupted all your cache state. Another really big challenge, which is very difficult for software developers to deal with, is figuring out where that code should run, right? In the case where we're spinning, obviously we're going to route the reply to some request back to the core that's spinning. But now it's quite unclear, should I wait for the core that previously ran this code to become available and for it sort of to block again because it's run some other piece of code? Or should I spin up another core that's now going to have cold cache state and going to have to take a lot of misses to try to run that same code? And that's a very difficult decision. And today, the default answer in Linux is if there's a core available, let's spin up another core. And so almost invariably, you're going to end up executing a lot of these replies with cold cache state if you take this approach. So this is trading latency for efficiency. And the effect is to get enormously high latency tails. So what can we do about this, right? We'd like to find a way to make microsecond scale IOs actually only take microseconds and yet still efficiently use our CPUs. What are sort of the research directions that hopefully I and my students will start pursuing, and I would encourage all of you to think about. So what can system architects try to do, right? So one idea perhaps is maybe there should be more hardware threads, right? The problem partially is that software is relatively inefficient in swapping out one piece of work for another. Maybe we could do better if hardware were helping borrow some ideas from GPUs, which have lots and lots of threads and always have something else to run. So that's sort of one direction that perhaps we should pursue. Another direction that perhaps we should pursue is thinking about this cache thrashing problem. If I do want to go run some other piece of code that I plan to interrupt very soon, is there some way I can magically protect the state that I want to have still present when I come back and run that continuation after the I/O comes back? Or is there some magic I can use to restore that state and have it sort of brought back into my hardware caches so I'll be able to run very efficiently when I resume execution? Sort of another big challenge here is this reply dispatch problem, right? How do I decide where code, after an I/O comes back, where that code should run? Maybe hardware can help, or maybe programming languages can help, and software systems can help. Is there perhaps hardware support that could help us realize, okay, this reply is going back and is associated with this state that's on core 3. How can everything from the network all the way through understand this piece of data wants to end up near core 3 and execution wants to resume at core 3? And sort of just thinking more fundamentally about this scheduling problem of when is the right answer to stall and wait and run on the same core, and when is the answer to spin up more parallelism and actually pay the price of bringing state over to a new core so that I get more parallelism, but now I'm going to pay for cold execution. And then the last point here is, I've said at the beginning, one of the challenges is we would really like to provide a synchronous programming interface. Programmers understand how synchronous I/O works. It's a very clean abstraction. You have straight line code. You can understand what it does. But today, if you want to write a high-performance service, if you're implementing Facebook or Google Web Search or Bing, you're going to end up writing asynchronous code that looked like that spaghetti that I showed you in the eye chart with lots of callbacks and a great deal of complexity because you can't afford to have a thread for sort of every piece of user's context that you'd like to keep together. But perhaps we as language designers and as system designers can make it easier to write asynchronous code. Maybe we can provide synchronous abstractions with sort of the performance of asynchrony. I would point to the Go programming language as one example of an attempt to do this with cooperative multi-threading, where sort of in user code, we try to understand when is it time to switch threads. And so there's a big opportunity for perhaps better language support or faster software threading approaches that don't involve the operating system and the operating system threat scheduler, which has no idea what you'd like to do in these sort of low latency I/O situations to figure out where things should execute. And so, my call to arms here is I think there's a pressing need for ASPLOS research, right? For architecture, programming languages, and operating systems to come together and figure out what is the right abstraction and what is the right way to write high-performance software that does frequent low-latency I/O and yet get it to run with high CPU efficiency. So given the time constraint, I'm going to stop here and just sort of conclude. I think there's really cross-cutting challenges here that go beyond hardware architecture. There's really opportunity to do research and figure out how we should write large-scale software systems for this new world where we have microsecond scale I/O. What I haven't really talked about is this business of the tail at scale, where rare events really are the common case. There will always be a 99th percentile tail among the 100 servers that you contact for a request. So now we don't have to think about sort of making the common case fast. We really need to reason about why are rare events happening, what can we do about them. And the last observation I'll make as I leave you is there are a lot of cores on modern servers, right? We have over 100 cores in the next generation of server, and yet sort of Linux is still using the same scheduling mechanisms that pretend that every core cycle is precious and there's only 4 cores out there, and we have to do everything we can to spin up a new core every time there's a piece of work to do. Maybe we should think about something different. So thanks a lot.
All right, Boris, while you're setting up, we'll take 1 question in the transition.
Too early in the morning.
Oh, it's sort of interesting that the examples you presented earlier about how to hide latency through parallelism, none of them really help with the problem of reducing the tail latency. They're all aimed at better efficiency.
That's because we only got through half the talk. No, you're right. You're absolutely right. That's a correct observation.
It's a tricky trade-off you're going to have to figure out. How to, even those techniques, how can you also simultaneously try to reduce the tail?
I agree, and I think the tail is an enormous challenge, and even understanding where the tail is coming from is an enormous challenge, right? I mean, what is it really? So we did measurements recently of sort of network I/O, and just back-to-back servers, you have a median latency of 50 microseconds. Every now and then, it takes 10 milliseconds to send a packet. What in God's name happens, right? And the answer is probably the operating system screwed you somehow. We really need to figure those things out and find ways to address those sort of obscure tails.
Thank you again, Tom. Yes?
Okay, thanks. Cool. Okay, great. Thank you very much, everybody. It's a pleasure to be here. I have to say that Kathryn's compilers class was actually really fun. I may actually remember a few things. Okay, so this is a perfect, Tom's talk was a perfect segue into mine because he talked about killer microseconds. I'm going to tell you that even microsecond sucks. We want to go faster than that. So obviously, data sets today are big. That's the exciting thing, right, in our world. They're getting bigger, and increasingly we want to do things with this data at online latencies, right? So if you want to work at online latencies, obviously what you're going to do is keep the data in memory, right? The problem is that if you look at a single server, there's not a lot of memory. Memory is precious. So and the data is growing. It's growing fast, right? So you need lots of memory and correspondingly lots of servers. Okay, so if you look at workloads like key value stores, various graph-based workloads, right? You have these large distributed data sets. You got to communicate, right? And in many cases, communication is actually in the critical path. And so what you really need is low latency remote memory access. Okay, and that's really what this talk is about. So now, if you look at a data center, right? There were a couple of talks throughout this really awesome event that alluded to the fact that today's data centers are freaking enormous, right? Enormous. And so just the speed of light of crossing the data center will easily add up to microseconds, okay? So forget about, sub-microsecond access latency if you're going across a data center, right? So that naturally takes us to a rack scale unit as sort of a natural physical form factor within which you can get, at least in theory, incredibly low latencies because, well, speed of light is really no longer an issue, right? It's fast enough. And so the question is, how do we actually architect such a system? Okay? And by the way, just to be really clear, I am saying rack scale. I'm going to keep saying rack, for the duration of the talk. But I mean, that's not like set in stone, right? It could be a chassis, half rack. It could be a couple of racks. The point here is some, physically tight unit of compute consisting of a bunch of servers. Okay. So what are the options, right? Okay. So we can look at cache coherent NUMA servers. Oracle would love to sell you one of these guys, right? The reason they would love to sell you one of these guys is because they're going to charge you a hell of a lot of money for this. So, these are scale-up system, right? For large SMP system, this is going to cost you an arm and a leg and a bunch of other body parts. It gets you ultra-low latencies, right? So processors are tightly coupled using a NUMA fabric. They issue loads and store, go straight to remote memory if necessary, right? Cache coherence, it's all taken care of, really nice. Comes with a couple of issues, right? So cost is the foremost one, and there is a reason why the cost is high. There's a reason why cost is high, right? This is essentially a custom-built, large-scale specialty system. You got to have a scalable coherence protocol. These things are really hard to verify, right? So hard to design, hard to verify. There's a lot of money that goes into it, and then at the end of the day, you have a working system. It's a massive fault containment nightmare, right? It's a single OS image running on a lot of cores and a lot of memory, right? If one of those things goes down and takes a chunk of your system memory with it, what happens to the rest of the system, right? So a lot of the money actually goes to guarantee hardware resiliency and things like that, so that if a piece of a system goes down, the system can stay up, okay? This is nuts. You're not going to put this in your data center, but it is very low latency. Okay, at the other extreme of the cost complexity spectrum is your, commodity Ethernet. Right? Well, this is cheap. It's commodity, right? It ain't going to get you low latency by a long, long margin, right? So, what this chart basically shows is what happens to request when it's sent from one server to another using, our good old Ethernet, right? So the red lines, red arrows basically mean slow. So an app, you can communicate, let's say, over sockets or whatever, right? You issue, you want to communicate, you issue a request, trap into the kernel, context switch, TCP/IP stack runs microseconds, right? Many microseconds, maybe milliseconds, right? At some point, you got a network packet ready to go. You ping your NIC. Right, go over the PCIe bus, get the packet. This is a pretty dumb device. There's not a lot of worker time that's spent here, right? You go over the switch, NIC on the other side, interrupt the CPU, pull the packet over the PCIe bus, TCP/IP stack. I mean, when all is said and done, you're talking about, if you're lucky, tens of microseconds, right? Possibly milliseconds. Okay, very, very, very slow, right? So, to put some numbers here, local memory access is order of, 50, 60 nanoseconds, right? As I said, TCP/IP stack without offload, tens of micros probably. PCIe interface, half a microsecond for each crossing, right? So, that's a couple of crossings, round trip, 4 crossings, that's 2 microseconds right there, right? All of these things add up. Okay. We can do a lot faster, a lot better with still commodity components at a decent price premium, but still commodity, right? So what you can do is you can get your some sort of RDMA solution, so InfiniBand or Rocky, which is RDMA over converged Ethernet, right? And so the number one thing that this thing buys you is basically a kernel bypass. Okay, so you don't have to trap into the kernel now, and your network stack offload. Now, you're not running TCP/IP any longer. You're running either InfiniBand or another protocol, but that's hardened into this thing that is no longer a NIC. It's called an HCA, host channel adapter. There's a lot of logic. It's a fat piece of silicon, but this thing is going to run everything in hardware fast. Okay? So, this gets you a couple of nice things. There's still overheads, right? That's the red stuff. So you still have the PCIe crossings, several of them. You still have the switch. Best case solution, you get a couple of these HCA switches, HCA cards, and you stick them back to back with nothing in between. Okay, and so the number you get is something on the order of 1.2 microseconds. Okay, for a single cache line remote read. Okay, single cache line remote read. Okay, not bad, but it's about 20x of local DRAM, right? 20x is, it's a big difference, right? Can we do better than that? Well, one thing to notice is that the PCIe interface is in the way, right? Well, it turns out that there's another set of commodity solutions that can take care of that problem, right? And so that's, there's a breed of emerging servers that tightly integrate the fabric sort of right into the box and run it straight into the sock, right? So AMD C-Micro, RIP, used to do this. HP Moonshot is doing this. And so, this takes care of the PCIe problem. Unfortunately, at least in existing solutions or in recent solutions, the NIC was dumb. Calcita also had something very similar to this, for those of you who are aware of that, right? And so basically, you're now, again, you're back to running your TCP/IP stack in software, and so you're back to mini microseconds, okay? Okay, so kind of recapping all of this stuff, kind of summary of sources of latency, TCP/IP stack, right, running that in software on major killer, PCIe bus, couple of microseconds for a round trip time, right? That's a big deal. And then you have top of the rack switch. When we started this research, we thought this was a big deal. I think that silicon vendors have gone a long way toward making, towards sort of data center friendly, and so the latencies have come down considerably. My understanding is, I've never benchmarked a Tor switch. What I'm told is that today you can buy these things with about 100 to 100 nanosecond latencies. If somebody can confirm or disconfirm, that would be cool, right? So it's not bad. Okay, so kind of scale out NUMA, right? This is our project that we've been working on for a couple of years now, is a ultra low latency remote memory access architecture for rack scale class systems. Okay, so the key components of scale out NUMA, and I'll spend a few minutes overviewing them. Obviously, it's a short talk, so if you have any questions, just follow up with me offline. But it's basically a memory fabric, so NUMA, right? A memory fabric of SoCs. It's an RDMA-inspired programming model. I'll say a couple of words about this in a slide or two. And then the thing that really makes this tick and makes this super efficient and an actual research project, because everything else is largely off the shelf, is this coherent on-chip integrated piece of logic called the remote memory controller, which is basically a combination of an on-chip network interface, protocol controller, and there's some other cool things that I'll very briefly touch on, right? But its basic job is to expose remote memory to user software and to essentially do a very simple protocol offload. Okay, so very quickly, let me say a couple of things about each of these components. So how do I address these three sources of latency? User-level messaging, integration, on-chip integration, and a NUMA fabric. Okay, so user-level remote access. So we do essentially what RDMA, InfiniBand do, which is one-sided operations, right? That means that user code explicitly issues remote accesses in software, right? So we can do remote read, remote write, remote atomic. We support a super minimalistic subset, unlike what you find in RDMA standards today, right? And this is what makes us very lean and very efficient. Anything else you want to do, you got to build in software on top of this. The semantics are copy, right? So when you do a read to remote memory, that memory will always serve you the most up-to-date version. But what you get is a copy now, so maintaining coherence is up to the programmer. Now, one of the key questions that we wrestled with is why not, or should it be a load store machine for very low latency? And in fact, HP's Moonshot is a load store machine, right? It's a rack scale or whatever, chassis scale load store machine, right? Well, what we find is that an out-of-order window really limits concurrency. Tom Wenisch also spoke to that extent a few minutes back, right? So this limits your bandwidth. This doesn't limit your latency. This really dramatically limits your bandwidth. And it also precludes exposing richer semantics of software, which is something we would like to do and can do using the one-sided up approach. Okay, let's see. So it's an RDMA-like queue-pair model. So basically, there's a work queue, you strip a request to that. A network interface picks up a work request, sends it over a fabric, direct memory access at the destination. So there's no interrupting of the CPU, returns the request back, writes the completion queue, to notify the core, and at some point, the core will poll on the completion queue and discover that the request is completed. Obviously, this is very natural to do this asynchronously, so you can get high bandwidth out of the system. RDMA does this today, right? This part is really not new. What is new and exciting is this on-chip integrated network interface, okay? And its capabilities. So let's see, I'm starting to run out of time. And so I really want to spend just a minute talking about that thing. So it's this is our sort of network interface remote memory controller part. What it does is exposes remote memory to user software. It picks up, so it monitors cache traffic, monitors coherence traffic. It discovers work queue requests generated by software threads, converts them into network transactions, does this all in hardware. If the request span multiple cache blocks, so it's an object, it will actually unroll them and generate a bunch of cache line size transactions, because again, it's a NUMA fabric, right? It's cache line sized operation. It will directly access application data, be it at the remote side or at the local side, let's say when the read comes back, on behalf of the application, okay? So essentially everything associated with remote access is fully offloaded. Okay, and then rack-scale NUMA fabric, this is not exciting. This is just NUMA, right? So it's non-discarding, cache block-oriented protocol and physical layer. Okay, so high-order bits, we can get ultra-low latency remote memory access. So what we've done through a lot of analysis, simulation, is shown that roughly something on the order of 4x of local DRAM is possible. So it's on the order of 220 nanosecond to a nearest neighbor, assuming some sort of a point-to-point topology. Load store interface is not necessary. It buys you very little latency reduction. Coherent on-chip integration is really the key to efficiency. This is what enables ultra-low latency core-to-network interface communication. Now, you actually have to put thought into how to build your network interface, especially in the many-core processor, okay? You can read our papers on that. And this opens doors to richer services. I wish I had time to talk about that. I have a couple of slides, but Kathryn has like this big red stop sign on her laptop, so I'm just going to stop right here. So.
Thank you, Boris. So one question for Boris while we're setting up. Mark?
Yeah, do you see the RMC collaborating with the thread scheduler so that you can hide that extra latency?
So the RMC supports as many threads, as many queue pairs as you want to throw at it. And this is one of the benefits of actually being on chip and coherent is because you can just use a virtual memory, right? So queue pairs are just memory, right? They're not special. And so in that sense, if you want to hide latency by having a few threads and each thread generating a ton of outstanding transactions, that's fine. If you prefer to hide latency by having lots of threads operating in a synchronous manner, that's fine. We're actually ambivalent to that.
So it's my pleasure to introduce our next speaker, Kathryn Strauss, who's been working on DNA computing, but today she's going to be talking storage, and today she's going to be talking both about that project and non-volatile memory. So really looking further out how we can store a lot more things and get low latency eventually, but not yet.
All right, so when Kathryn asked me to switch with Doug, I decided I needed to change the title of my talk. So instead of getting Doug talking about computing, you get me talking about memory. It's approximately the same talk, but not quite. All right, so talking about memory, future of memory. We know that scaling is getting harder. Scaling memory, not only computing and continuing Moore's law, but also scaling memory is getting harder. And we see evidence of that by looking at the roadmap for memory. It used to double in capacity every 2 years. Now it's doubling every 3 years. Flash had to go 3D because it was getting too expensive to scale flash cells to smaller feature sizes. And so we're seeing all these difficulties in scaling memory. And one of the major trade-offs in scaling memory is this trade-off between reliability and cost. And what manufacturers do now is to hide failures and incur cost in trying to hide these failures. And so in this talk, I want to provide an alternative, which is really surviving failures and not trying to hide them always. And one way in which you can do that is by using wearable memories, meaning memories that wear out as you use them, including using these memories for main memory. And so what I want to talk about is how to do that in a way that integrates well with the system. So the first thing to think about is what are the desirable properties we want if we want to live with wearable memory. So the first one is dynamic failure recovery, meaning as the system runs and memory wears out and the failures happen as the system is running, how can we actually continue system operation? And here's one sort of simple way, one way to keep the system running. We have our wearable memory that's used as main memory, but we also have a tiny little piece of memory that is DRAM, which could be DRAM that we use today, which is 100% precise. And we put our critical data, meaning all the code that's required for recovery, for example, from an interrupt, and all the state that's required for recovery for a memory failure in this part of memory. And add codes to, that recovers from failures that happen as the system runs. Another desirable property is graceful degradation and also reasonable memory longevity. So I just want to use this graph to illustrate that. Here I'm showing in the x-axis writes to memory, and on the y-axis the useful memory capacity we have. And right now what we have is the DRAM line, which is that black line on the top. It's always guaranteed to be full capacity and fully correct. And when we get into the wearable memory world, what we have is this curve where memory gracefully degrades, but we want to push the green line as far as we can. So if we look at the system today and how we would recover from one of these failures that happen when a particular bit in memory wears out, what we have is the system is organized into pages, right? And these are OS granularity pages that I'm talking about. And when you get a failure, what we have to do is essentially throw away that entire page. And that's quite wasteful. There are still lots of bits in that page that are alive. And so we're throwing away a good chunk of memory for no good reason, only because that's what our systems today can support. So our first attempt to fix this problem was to come up with error-correcting pointers. And the concept here is just adding metadata to the memory so that when you get a failure, all you have to do is to add a replacement bit and point to the bit you're replacing. But eventually, as you get more failures, you run out of resources to correct that, and a whole line becomes damaged, or you can't really use that line. And with today's systems, you have to again throw away that entire page. And so this again is very wasteful. So I want to give you an overview of 3 different techniques in which we can reduce that waste. And here we're really looking at reducing the waste, recycling bits, and reusing the memory. So the first one I want to talk about is extending the memory lifetime by reviving dead blocks. So the idea here is you have 2 pages, they have some failures, there are some resources to correct those failures, but eventually there's an unrecoverable failure in a page, and so you have to disable that page. However, there's still many good bits here that can be used to correct other pages that haven't failed yet. So the idea here is essentially you get a new failure in in another page. That page is still good. It still has, it still carries data. It still stores data that's useful for the system. And now we're going to use bits in the other page to error correct for that first page. And so we're surviving that failure by reusing some of the bits in pages that are dead. And with that, and with the help of quite a bit of coding theory, we were able to get quite an improvement in the longevity of pages. I'm not going to go into a lot of details since I only have 15 minutes and I'm trying to pack a whole hour here, but these are the results if you're interested. There's a lot more on our paper. The next one is how to leverage and reduce the granularity of failures so that we can reuse more of the bits in pages that have failed. So the concept here, the idea here is to use the memory abstraction that a managed runtime offers to hide the failures. And with that, not require any changes from the actual application. And so here's what this system would look like. It's the same system I showed you before, where there's where the critical data is stored in memory that does not have the wear problem. And in addition to the critical recovery data, what we're storing here is also a map of which lines in memory have failed, so that we don't have to do that throwing away of pages at the OS level. We're actually doing the throwing away at the managed runtime level. And so as failures happen in our wearable memory, that map is constructed, and this is responsibility of the OS. And then whenever the managed runtime allocates memory, the OS passes that map to the managed runtime so that the managed runtime knows which regions of memory to avoid. And so the next question is, what kind of allocator do we want to use? And if we use contiguous allocation, it has good locality, but it cannot really step very well over the holes. It's not straightforward. A free list can do that, but then you lose on locality. And so we decided to use IMIX, which is a mark region memory allocator, to help us with that. And we chose IMIX because it has these characteristics plus the best published performance in the literature. And we were working with Kathryn and Steve, who are the experts on IMIX. So let me just quickly show you how IMIX works. So we have pointers, and this is our memory space. And IMIX is organized into blocks of memory, and within those blocks, it has lines. And that's where you allocate the object. So we start by allocating in a region by bumping a pointer, and we allocate until we hit a piece of memory that's occupied by an object. And at that point, the pointer jumps over that area and starts allocating in the next free area. And so once we have failures in that memory, essentially what we have is a bunch of areas that appear to be occupied, but they're really failures. They're just as unusable as the occupied areas before, but they are failed pieces of memory. But IMIX works in the same way. It's just skip over areas of memory that are unavailable. And so it allocates around. And there's quite a few more subtleties about doing this, but I just wanted to show you a few results. First of all, there are no overheads in the absence of failures, which is pretty good. And then the overheads when there are failures, even when there's a high rate of failures at around 50%, we still get pretty low performance overhead because of that. And then the last mechanism I wanted to talk about is approximate storage. So here the concept is that not all applications need memory to work at 100% precision. And so there are applications like machine learning, sensor data processing, image and video processing that already have some approximation inherent to them. And so they don't need 100% precision from the memory either. And then you can trade off for different desirable characteristics. In this case, we were focusing on denser cells. So the idea is that if you have a cell that is a multi-level cell, meaning you can store multiple bits, by dividing a range of resistances, you could actually pack those different states in and add more states to the top so that you get higher density. But what you lose is precision in writing these cells. And so sometimes the value of that cell is going to be flipped. But that doesn't matter because applications can actually, certain applications, not all, but certain applications can tolerate that. So in terms of density, what we get is about a 50% improvement in density at about 5% loss, which is not a lot for certain applications. Now, there's one particular type of data that we wanted to store that didn't quite work that well with that kind of approximation, which is encoded images. And here's the region. If you have an encoded image, if you have a raw image, which is what I'm showing here on your left, and a few of the bits are broken and you don't quite have that value in your memory, then a few pixels are going to be wrong, but that's okay because you can't see it. Now, when you encode that image, what happens is that you're summarizing, you're really packing in that information into a much more compressed piece of data. And what happens is that certain bits are much more important than other bits. And so if you have corruption of some of the important bits, you actually get corruption of your whole image. And I'll show an example in a second. But the idea here is to actually organize the bits and reorganize the algorithm, the encoding algorithm for the image, and pull out the important bits so that we can error correct the most important bits, the darker bits there, and error correct just a little bit important bits, and not error correct at all the bits that are not important for quality, for the quality of your output or the quality of the image. And so this would essentially boils down to providing different level of protection for bits that have different importance. And this is what we see. So here what I'm showing is on the left, a result for memory that's not very dense, where we only have 1 bit per cell. And we're fully providing error correction, so that the image is perfect. If we pack those bits, and we pack, instead of packing 1 bit per cell, we actually pack 3 bits per cell, what we get, and don't error correct, what we get is the second image, which is completely disfigured. And so if we now add error correction to the entire memory, what we get is the third image, which is perfect again, but we get some reduction in the density we had for those cells. And finally, if we do it selectively and only error correct the bits we actually need to error correct, what we get is pretty good quality. That's about 1 dB of degradation in the image quality, but we recover almost all of the density benefits that we had in the first place. So with that, I see Kathryn looking at me, and I'll just take any questions you have. And I'll welcome you. I know this was, again, just like Tom, this was a quick overview of an hour talk. So if you're interested, there's plenty of literature to read about more details. Thank you.
One question. The approximate memory stuff is kind of interesting because it kind of points up this question of, in some sense, you can afford to lose a bunch of bits if your representation is inefficient in some sense, right? So I'm curious whether you have any insights about whether those kinds of representations, like the images you're looking at that have some important bits, some less important bits, are fundamentally inefficient. You might drive us to something more.
Yeah, so the less important bits, once you lose them, you lose some information. You're actually losing that information. But at least you can put them into categories, and depending on the algorithm, you can actually pull those bits apart. And so for images and for this particular codec that we looked at, we could actually pull them apart. You're still losing information, but there's different levels of information you're losing. So I don't know if that answers your question, but yeah, I'm happy to.
I think you could further compress and make all the bits more relevant. From an information standpoint.
Yeah, well, I'll just say we used code that is actually a standard, it's JPEG XR. So it's not like it's unoptimized or anything like that. This is actually code that has been extensively optimized by coding theorists. But yeah, you have an interesting point.